right, so this is the first one we're going to look at. So a runner is running down the first baseline at 20 feet per second. Here, I can make him run. This is actually kind of funny how this goes. Like, he just keeps on going. And I get that, like, that's what you do in real baseball too, because you don't want to slow down as you get there. You want to keep on going, but it's just funny that he like keeps running off of the screen there. Okay, anyway, he's running down the first baseline from home to first, 20 feet per second. How fast is his distance from second base changing? So even though he's running towards first, his distance from second is also changing because he's moving, he's running. When he is 10 feet from home plate, and we won't do the other questions again, we're just going to do the problem once. And then also notice for the baseball diamond, the bases are 90 feet apart from each other. And they call it a baseball diamond, but it's actually mathematically a square. It's a baseball square. So 90 feet on one side, he's running from home to first. All right, let's draw a picture of what is going on in this problem. So go ahead and draw yourself a baseball square. And so this guy is running from home to first. So he's somewhere in between here. This is not going to be to scale. I'm just going to put him right there. It doesn't matter. He's somewhere in between. He's running at 20 feet per second this away. So this distance is changing. So I'm going to call this distance from him to first base, I'm going to call that x. And then we're being asked about how his distance from second base is changing. So I'm going to go in and draw a line from him to second base. That is also changing, so I'm going to call that y. Again, anything that's changing, you need a variable for. And again, I know he's running this way, but that means this distance is going to be changing as well. And then lastly, we have this distance from first base to second base is going to be 90 feet. I always joke when I teach this problem, like, the bases aren't moving. Like, no one picked up second base and ran away with it. But I think that would make baseball a little bit more interesting, don't you think? If like the bases were able to move too. Anyway, they're not. But I just always think that for this problem. And 90 feet is constant. That is not changing. And so what we want to focus on is this right triangle. So I understand there's like a whole square there, but we want to look at that right triangle. All right, so let's list out what we were given. The guy is running at 20 feet per second. So that's a rate. How will I label that 20 feet per second based on what I've written in my picture here? Good, awesome. dx dt, perfect. Nice job, guys. dx dt. And will it be a positive or a negative for that rate as this guy is running along here? Will it be positive or negative? And yeah, good. It's going to be negative. So negative 20 feet per second. And it's because that distance between him and first base is shortening. That's decreasing. All right, cool. Our question mark, what we're asked for is how is his distance from second base changing? So dy dt is the question mark. And that is also going to be negative. Again, I know he's running this way, but as he gets closer to first, the distance from second is also going to be less as he goes that way. And then we have to pause at a certain moment, and this is a little tricky. The distance that they gave us for like where like at this particular moment, they said when he's 10 feet from home. So that's this distance, 10 feet from home. So x is not 10. If he's 10 feet from home, what is x going to be? What is our x distance if he's 10 feet from home? Good, perfect, nice job, guys. That'll be 80 feet. Because the bases are 90 feet apart, so if that's 10, then x has to be 80. Good. All right, so we have a picture, we have all our information. Now we're going to write out a relationship between the variables, and it's going to be Pythagorean theorem. So this will be x squared plus 90 squared equals y squared. And so then we're going to do the derivative with respect to time. So this is 2x dx dt. 90 squared is a constant, so that's gone. Again, the bases are not moving. And then 2y dy dt. And so again, I'm going to cancel out the 2's just to simplify that down. And then we're going to plug in everything we've got. So x is 80. dx dt is -20. I do not have y, so we'll come back to that. And dy dt is what we're looking for. So if you're missing something, you're going to go back to this original relationship and plug in what you have. So x is 80. If I plug that in, I'm just going to do this as a side problem over here. 80 squared, that'll be 6,400. Plus 90 squared will be 8,100 equals y squared. Adding those together, gosh, what is that going to be? 14,500. 8 and 6 will be 14, and then 500 equals y squared. That is not a perfect square, so I'm just going to leave it as square root of that. Again, you don't want to touch a calculator unless you absolutely have to. I'm sure I'm going to need to with one of these problems at some point, but you're better off just leaving it alone. Also, if the question's non-calculator, then you can't use it anyway. All right, and then last step, we're just going to divide that over. So this will be 80 times -20 over this square root. You don't have to simplify that down. You don't have to do anything else to that. The only thing we need are units, which are feet per second. And so it did come out negative like we were expecting it to. All right, so that one was the baseball problem. So let's try another one. All right, so this one is about a balloon that is being inflated, because all balloons are perfect spheres, as we know. It is a spherical balloon. It is being inflated at 10 cubic centimeters per second. And I wish that it popped at the end of the, I always wait for it to like pop. I wish they had done that in the animation. I think that would have been funnier. But anyway, it's inflating at 10 centimeters cubed per second. So use that cubed as a clue for you. Cubed means it's talking about volume. So this is the rate for the volume of air inside the balloon. So how fast, this is our question mark value, how fast is the radius changing when the diameter is 1 centimeter? Okay, so how fast is the radius changing when the diameter is 1 centimeter? So you can draw a picture for this one if you want. I can't draw a sphere. This is actually a problem where a picture isn't necessary. I can draw a circle, but trying to make it a 3-dimensional sphere is not, I'm not going to embarrass myself by trying to do that. We actually don't need a picture necessarily for this one. I'm going to go ahead and list out the information. They told us it was filling up at 10 centimeters cubed per second. So that is the rate of change for the volume. So that is dV dt, V for volume. And it's positive because it is, filling up. Now they're asking us for our question mark value here. What is the rate of change of the radius? How quickly is the radius changing? So what is going to be our question mark value here? How will I label that? We want to know how fast the radius is changing. Good, nice job, guys. dr dt. And should it be positive or negative? Yeah, good, positive, awesome, because the balloon is filling up. Nice job. All right, and then we have to pause, and it said when the diameter is 1 centimeter. All right, so here, this is a little tricky. They gave us the diameter, but we're talking about the radius. That's okay, we can get it really easily. If the diameter is 1, what is the radius? Oh, careful, I think you went the opposite direction. Yeah, there we go. If your diameter is the whole way across. So if that's 1, the radius will be half of that. So half a centimeter or 0.5, 1/2, 0.5. Yes, that happens to me all the time. All right. And that bothers you guys way more than it bothers me. I just like when people talk to me, especially in this kind of an environment. I love when you guys type in the chat. It makes me feel like you're here with me. All right. Now this one, the relationship between the variables, you're going to need volume for a sphere. I would not make you memorize that. I'm going to give you volume for a sphere. It is volume equals 4/3 pi r cubed. So that one I would give you. All right, so derivative, this is going to be dv dt equals. Now, when you multiply this 3 down for the power rule, the 3's are going to cancel, which is convenient. So this will be 4 pi r squared, and we drop a degree, and then dr dt. And this is actually a rare situation where we have all the information. We're not going to need to go back and find anything, which is kind of nice. dv dt is 10, and r is a half. And then you just have to get dr dt by itself. So you're going to divide all of this over. Now look, guys, I know some of this stuff simplifies. I'll do that too. But here's my suggestion. Just divide it all over and don't even worry about it. Like, this is a perfectly acceptable answer for free response. There's nothing wrong with that. So just don't, just hands off, I guess is what I'm saying. Because if you try to simplify it down and you make a mistake, then it's going to be wrong. Here, I will simplify it just for the sake of going through it. If it was multiple choice, you'd have to keep going. So a half squared would be a fourth, and a fourth and 4 would actually cancel out. So this would reduce to 10 over pi. But again, if it's free response, I'd want you to stop there. And then units, this is also a little tricky. We were given centimeters cubed per second, but the cubed is because that was a rate for a volume. We just found a rate of change of a radius, so ours will just be centimeters per second. Again, squared is for area, cubed is for volume. All right, and we'll do one more and then we'll do another break here. All right, so let's read what is going on with this one. And I know that's like super intense. It's like, oh my gosh, are they gonna hit? And then it's anticlimactic. There's like no collision. All right, at time 0, a car is traveling west at, now we're gonna use the feet per second because everything else in the problem is in feet per second. So just kind of ignore those miles per hour. Car travels west at 96.8 feet per second towards an intersection 400 feet away. At the same time, a truck is traveling south at 44 feet per second towards the same intersection 250 feet away. Let's pause there and think about that. They gave us a lot of information. They gave us the rate for the car and how far away the car was. And then they give us the rate for the truck and how far away the truck was. So they gave us all of that. And the question is, how fast are they approaching each other at that time 0? All right, so let me go ahead and, oh, this is kicking me out anyway. Let me stop sharing here. All right, so we're gonna have a right triangle. And in this problem, nothing is constant. Everything is moving. So I'm gonna need variables for all the sides of the triangle. In the baseball problem, the bases weren't moving, so that was constant. If you remember the last time, the ladder problem, the ladder was not changing size, so that was constant. When we did the boat problem, the dock was not growing, so that was constant. In this problem, everything's moving, so they are all variables. So let's do the car first. Car is going this way, and the car's rate was 96, I have it written down here somewhere, 96.8 feet per second. So dx dt is negative 96.8 feet per second. It is negative because that distance is decreasing. And at the moment when we've paused, the car is 400 feet away. So that was for the car. The truck is moving this way, moving south, and they told us the truck's rate, so this will be dy dt, is 44 feet per second. That is also going to be negative because that y distance is also shortening. And they told us that the truck is 250 feet away. So that's all the information that they gave us. They gave us a lot, which is good because we're going to need all those numbers. And they're asking us how quickly is the distance between the two vehicles changing, and that's going to be the dz dt. And so should that be positive or should that be negative? Yeah, good. That is going to be negative. Because if the car is going this way and the truck is going this way, they're getting closer to each other. So that distance z is going to be getting smaller and smaller. Until we're worried that, oh my gosh, they might actually hit each other. All right, so we're expecting that to be negative. And then our relationship between the variables, again, it's going to be Pythagorean theorem. So x squared plus y squared equals z squared. Again, there's nothing constant here because everything is moving. And so this derivative with respect to time, so 2x dx dt plus 2y dy dt equals 2z dz dt. It's actually really repetitive because they all end up being the same. And then if you go through and divide by 2, all the 2's are going to cancel. So I'll just go ahead and get rid of it. And then we're at the point where we're trying to plug stuff in. So x is 400. And dx dt is this negative 96.8 plus y is 250 and dy dt is negative 44. Z I do not have, so we're going to have to come back to that. And then dz dt is what we're trying to find. So if you're missing something, go back to the original relationship. We're going to plug in what we have. So x is 400. So 400 squared plus y is 250. So 250 squared equals z squared. And here's where I am going to pick up a calculator because these numbers are going to get a little bit large here. All right, so 400 squared plus 250 squared is 222,500. And then we're going to square root that. Now, that is not a perfect square, so I'm just going to leave it as that square root. I know that looks messy, but don't worry about it. That's what it came out to. And then your last step is just to get dz dt by itself. So we're just going to divide that over. Again, I would simplify none of this. I know that sounds like I'm telling you to be lazy, and sorta. I mean, you don't need to, so don't bother. In fact, I get nervous when stuff is simplified because then I'm like, where'd you get that from? I'd rather you just leave it like this. And then just units. So units for this one are feet per second.